Right now, as you watch this, the future of humanity is being rewritten quietly in labs, observatories, and think tanks across the globe. Not decades from now. Right now, in real time, breakthroughs are reshaping life as we know it. In this video, we'll explore 7 of the most astonishing scientific discoveries, from gene editing to black holes, neuroscience to renewable energy, and see how they are redefining what it means to be human. Stick with me until the end, because the final breakthrough may not just change how you live, but who you are. Section 1. CRISPR and Gene Editing. Imagine if life itself could be edited, not just influenced or nudged, but literally rewritten, letter by letter, like correcting a typo in a Word document. This is CRISPR, quietly transforming medicine, agriculture, evolution, and even our very definition of humanity. It all began in the 1980s with a scientist named Francisco Mojica, studying microbes in salty water. Nothing glamorous, just salt, water, and a microscope. Yet he noticed something strange: repeated sequences in the microbe's DNA, almost like Morse code, with fragments in between that matched viruses that had attacked the microbes. It was as if the microbes kept a photo album of past invaders inside their DNA, and Mojica had stumbled upon something extraordinary: a bacterial immune system written into life's code. Today we call it CRISPR, clustered regularly interspaced short palindromic repeats. A mouthful, but what it really means is that life has memory and can fight back. Here's how it works. DNA is the world's longest book, written with just 4 letters: A, T, C, and G. Viruses are hackers trying to sneak malicious code into that book, and normally, the cell just gets infected. But bacteria evolved something brilliant. CRISPR, a system that scans the entire book of life, finds the viral code, and then snips it out using a protein called Cas9, molecular scissors. Cut, paste, delete, rewrite, the book of life becomes editable. Mojica's discovery sat quietly for decades until Jennifer Doudna and Emmanuel Charpentier realized CRISPR could be harnessed for humans. Cas9 could be programmed like a GPS-guided missile, capable of changing 1 letter in a 3 billion letter genome with laser precision. Before CRISPR, gene editing was slow, clumsy, and expensive, like trying to edit a novel with a hacksaw. CRISPR made it feel like Microsoft Word with track changes. Since then, the pace of discovery has been staggering. In 2012, the first landmark paper showed DNA could be edited in test tubes. By 2013, human cells were successfully edited, and by 2016, CRISPR crops hit the fields, producing mushrooms that don't brown and corn that resists drought. In 2020, the Nobel Prize was awarded, and the same year, a woman with sickle cell disease became the first human to be cured through CRISPR, her genetic typo corrected and her pain gone. Today, CRISPR is everywhere, targeting devastating diseases like cystic fibrosis, blindness, and Huntington's, creating drought-resistant crops that need less pesticide, engineering mosquitoes to stop spreading malaria, and even being tested in space to protect astronauts from radiation on long missions to Mars. Some projects are even attempting to bring back extinct species like woolly mammoths, restoring lost ecosystems and slowing permafrost melt. Kits now cost under $200, and high school students are editing bacteria in their classrooms, proving that the next revolutionary mind in biology could be only 16 years old. Some researchers are exploring whether CRISPR can slow aging itself, literally buying time at the cellular level. Yet with such power comes profound responsibility. In 2018, a Chinese scientist announced the birth of the world's first CRISPR-edited babies, engineered to resist HIV, sparking global outrage. This wasn't just curing disease, it altered the human germline, changes that could pass down through generations. 1 wrong letter in our code could have catastrophic consequences. The question isn't just whether we can do this, but whether we should, and who gets to decide. And then there are stories like a young woman who had battled sickle cell disease her whole life, enduring endless pain and hospital visits, who volunteered for the first human CRISPR trial. Her blood cells were edited to fix the tiny typo causing her disease, and months later, she hiked for the first time, laughed with her kids, and lived without pain. That's not science fiction. That's reality. CRISPR has already cured a human disease, and the first domino has fallen. But the bigger story is even more profound. By opening the door to rewriting DNA, we've begun to rewrite evolution itself, and once you realize that life can be edited, you start to wonder what else in the universe can be rewritten. To find that out, we have to leave Earth entirely and peer into the abyss of black holes. Section 2. Black Holes and Cosmic Mysteries. Imagine standing at the edge of a cliff that drops into nothingness. You toss a rock over, expecting to hear it hit the ground, but it never does. That endless fall, that vanishing point, is the closest metaphor we have for one of the strangest objects in the universe: the black hole. A place where gravity is so intense that not even light, the fastest traveler we know, can ever escape its grasp. And here's the mind-bending twist. For decades, black holes were treated as science fiction, mathematical curiosities too extreme to exist. Yet today, they sit at the very center of our greatest cosmic discoveries. They're not just monsters in the dark. They are keys to unlocking the secrets of space, time, and perhaps even the birth of the universe itself. So what exactly is a black hole? To understand, we have to step into the life of a star. Picture a star 20 or 30 times the size of our sun, a giant nuclear furnace burning hydrogen for millions of years. But eventually, that fuel runs out. Gravity, which the star has been holding back with its fiery core, suddenly wins. For smaller stars, the collapse stops at a white dwarf or a neutron star. But for the biggest ones, the collapse never stops. Matter is crushed smaller and smaller, until it reaches a point of infinite density, a singularity. Imagine squeezing all of Earth down to the size of a marble. Rockets couldn't escape its pull. Now shrink it even further, so small, so dense, that even light becomes trapped. That's the moment a black hole is born. The boundary around it is called the event horizon. Think of it like the edge of a waterfall. From a distance, the river looks calm, flowing smoothly. But cross that edge, and the current becomes unstoppable, dragging you down. In the case of a black hole, the waterfall isn't water, it's space and time itself. Once you cross, there's no signal back. No return. For a long time, black holes were treated as fantasy. Even Albert Einstein, whose general theory of relativity in 1915 predicted them, doubted they could exist in reality. The math was undeniable, but the idea seemed too absurd. Yet, by the 1960s, astronomers began noticing stars behaving strangely, orbiting nothing. Something invisible and massive was tugging on them. The first real clue came from a system called Cygnus X-1. A star was clearly circling an unseen companion. At the same time, telescopes picked up streams of X-rays, radiation pouring out as matter was shredded and devoured by something invisible. That was humanity's first smoking gun. Black holes weren't just theory anymore. They were out there. And in 1967, physicist John Wheeler gave them a name: the black hole. Before that, scientists used clunky terms like frozen star or collapsar. But Wheeler's phrase was simple, dramatic, and unforgettable. Still, one question remained: how do you photograph something that swallows light itself? For decades, it seemed impossible. And then, in 2019, the impossible happened. The Event Horizon Telescope, a network of 8 observatories scattered across the globe, synchronized to split-second precision, effectively turned Earth into a planet-sized telescope. Its target, a black hole at the heart of galaxy M87, 55 million light-years away. What came back stunned the world, a glowing ring of light, bent and twisted by gravity, circling a dark shadow. Humanity's first ever image of the abyss. To appreciate how hard that was, imagine trying to photograph an orange sitting on the surface of the moon, using a camera the size of Earth. That's the level of precision it required. And the result was more than a picture, it was proof. Black holes weren't just real, they were exactly as Einstein's math predicted, a century earlier. But the revelations didn't stop there. In 2015, another breakthrough shook science. LIGO, the Laser Interferometer Gravitational Wave Observatory, detected faint ripples in the very fabric of spacetime. They came from two black holes colliding, billions of light-years away. Think of tossing stones into a pond and watching the ripples spread outward, except here, the ripples weren't in water. They were in reality itself. And the scale. LIGO measured distortions smaller than the width of a proton. To put that in perspective, it's like measuring the distance to the nearest star within the thickness of a human hair. When scientists converted the signal into sound, they didn't just see equations. They heard a chirp, the final death cry of two black holes colliding. For the first time, humanity had listened to the universe itself. And black holes aren't just strange in what they do. They're strange in how they bend time itself. Near the event horizon, time slows dramatically. An hour spent near a black hole could equal 7 years for someone far away. Hollywood captured this in Interstellar. Astronauts landed near a black hole, and by the time they returned, decades had passed for their crew. That wasn't fiction, it was Einstein's math, brought to life. To picture why, imagine a trampoline. Drop a bowling ball in the center, and the fabric curves. Place a marble near it, and it spirals inward. A black hole is like dropping something infinitely heavy. The trampoline doesn't just sag, it tears straight through. Space-time itself folds. And yet, the deepest mystery isn't what black holes swallow, it's what they might reveal. Inside, our best theories break down. Relativity explains the large. Quantum mechanics explains the small. But in the heart of a black hole? Both collapse into paradox. Some scientists believe that everything that falls in is encoded, holographically, on the event horizon's surface. Others think black holes could be wormholes, bridges to other universes, or even seeds for entirely new cosmos. Here's something wild. Without the supermassive black hole at the center of our own Milky Way, Sagittarius A*, our galaxy might never have formed at all. Black holes don't just destroy. They create. They shape galaxies, stars, and maybe even the conditions for life. A century ago, they were dismissed as impossible math. Today, we've seen them, heard them, and proven them. And here's the twist. If we want to understand the Big Bang, the ultimate singularity, the moment everything began, we may need to study black holes. Because in their darkness lies a reflection of the beginning of time itself. The darker the hole, the brighter the truths it may reveal. But if black holes hold secrets about beginnings, what about endings? What about the fate of our own world? To answer that, we have to return to Earth and confront a very different ticking clock, climate change. Section 3. Climate Change Science. Picture this, Earth, our only home, floating in the endless darkness of space. From a distance it looks serene, a glowing blue marble, delicately wrapped in white clouds. But beneath that beauty, something is shifting. Our atmosphere, once stable, once predictable, is warming at a pace unlike anything in human history. And the clock isn't just ticking, it's accelerating. But how do we know this? And why does it matter more than ever right now? To answer that, let's strip it down to the basics. Why is the planet heating up? It comes down to the greenhouse effect. Imagine Earth wrapped in a thin blanket, our atmosphere. Sunlight pours through, warming the surface. Some of that heat naturally radiates back out into space. But gases like carbon dioxide, methane, and nitrous oxide act like an extra layer of insulation. They trap heat. Think of curling up in a sleeping bag on a summer night. Instead of comfort, you overheat. That's what's happening to Earth. For millions of years, this balance kept the planet's climate relatively stable. Then came the Industrial Revolution. We began burning coal, oil, and gas on a massive scale. Factories, cars, airplanes, all of them pumping billions of tons of carbon dioxide into the sky. Today, CO2 levels sit at around 420 parts per million. The last time they were that high was 3 million years ago. When humans didn't yet exist, sea levels stood nearly 20 meters higher, and crocodiles roamed the Arctic. And the astonishing part? We've pushed the system that far in just 2 centuries. Every gallon of gasoline burned produces about 20 pounds of CO2, 10 times heavier than the fuel itself. Why? Because when carbon bonds with oxygen in the air, its weight multiplies. That invisible math adds up faster than most people realize. So when we talk about climate change, we're not discussing some abstract possibility in a far-off future. We're describing forces that are already reshaping the world we live in today. The data is unambiguous. Global average temperature has already risen about 1.2 degrees Celsius since pre-industrial times. That may sound small, but consider this. The difference between today's climate and the last ice age was only about 5 degrees. That shift was enough to cover half the planet in glaciers. Now, the Arctic is heating nearly 4 times faster than the rest of Earth. Greenland alone loses about 280 billion tons of ice each year, while Antarctica sheds another 150 billion. Together, that's enough meltwater to flood Florida annually. And it's not just ice. Heat waves once considered rare are now frequent and deadly. In 2022, India sweltered at nearly 49 to 120 degrees Fahrenheit. Crops withered, power grids collapsed, and hundreds of millions struggled to survive. Hurricanes grow stronger, wildfires rage hotter, droughts last longer. The fingerprints of warming are everywhere. Even the ice itself holds proof. In Antarctica, scientists drill deep cores, extracting cylinders of ancient ice. Inside are tiny bubbles, air trapped for 800,000 years. They're like time capsules of Earth's atmosphere. And those bubbles reveal something unprecedented. Carbon dioxide levels are now rising faster than at any point in that entire span of history. But warming doesn't strike evenly. Some regions are staring down risks so severe, they may become uninhabitable within our lifetimes. Take the Maldives, for example. These islands sit barely 1.5 meters above sea level. A single powerful storm surge could swallow entire communities. In Bangladesh, home to 170 million people, saltwater floods are poisoning farmland, not because of drought, but because rising seas turn the very soil salty. In the American West, reservoirs are vanishing, wildfires consume millions of acres, and Lake Mead, once the largest reservoir in the United States, has dropped so low that long-submerged ghost towns are resurfacing. And far north in Alaska, coastal villages like Shishmaref are literally sliding into the sea as the ground beneath them, once permanently frozen, turns to mud. Climate change doesn't happen nowhere. It happens at specific addresses, and some of those addresses are disappearing. And sometimes what emerges from that thaw is even stranger. In Siberia, melting permafrost has begun exposing the remains of mammoths and other ancient creatures, even reviving microbes and viruses that have been frozen for tens of thousands of years. Some of those organisms have reawakened, still alive after lying dormant since before human civilization began. Which raises the unsettling question, what else might thaw? This is where the danger deepens. Because Earth's climate isn't just a simple system, it's full of feedback loops. Once triggered, they don't merely respond to warming, they amplify it. Picture a long row of dominoes. Push one, and the chain reaction is inevitable. The Arctic is a classic example. Ice reflects sunlight, keeping the planet cool. But as ice melts, it exposes darker ocean water, which absorbs more heat. That extra heat melts even more ice, creating a vicious cycle. Permafrost works the same way. It stores twice as much carbon as the atmosphere itself. As it thaws, methane escapes, a greenhouse gas more than 25 times stronger than CO2. That methane accelerates warming, which thaws more permafrost, which releases even more methane. And the Amazon rainforest, once the world's great carbon sponge, is tipping under the weight of logging and drought, now emitting more carbon than it absorbs. These tipping points don't stay local. They ripple outward, tugging at the entire climate system. One scientist compared them to the dragon's tail. At first it looks harmless, just lying there. But step on it, and the whole dragon wakes. So, is it hopeless? Are we already locked into disaster? Or do we still have a way out? Here's the good news. Humans are problem solvers. And some of the solutions being tested right now sound like science fiction. Imagine floating solar farms, entire lakes blanketed with panels that generate clean power while reducing evaporation. Or urban forests, millions of trees planted across cities, cooling neighborhoods by several degrees. Even rice, one of the world's most important crops, is being re-engineered. Traditional paddies release vast amounts of methane. But new varieties can grow without flooded fields, cutting emissions dramatically. And then there's the surprising power of rewilding. When wolves were reintroduced to Yellowstone, they changed the behavior of deer. That simple shift cascaded through the ecosystem, reshaping forests and even redirecting rivers. Now imagine scaling that kind of restoration worldwide, using nature itself as an ally in the fight against climate change. Some scientists are even exploring reflective crops, plants with shinier leaves that bounce sunlight back into space. Agriculture as a kind of planetary sunscreen. But not all strategies are as gentle. Some go further, into the controversial realm of geoengineering, deliberately altering Earth's climate. One proposal: inject reflective particles into the stratosphere to mimic volcanic eruptions and cool the planet. Another: launch massive mirrors into orbit to shade Earth from the sun. But these ideas raise daunting questions. Who gets to control the thermostat? And what if cooling one region sparks drought or chaos in another? A less controversial but still ambitious idea is carbon capture. Machines designed to pull CO2 directly out of the air. In Iceland, a facility called Orca already scrubs about 4,000 tons of carbon dioxide annually, storing it underground as solid rock. It's a small step compared to global emissions, but it proves the concept works. And here's where the breakthrough comes in. New research suggests that direct CO2 removal may soon become cheaper than burning fossil fuels. That flips the entire game. Imagine a global economy where sucking carbon from the sky is not just possible, but more profitable than pumping oil from the ground. Suddenly, climate change isn't just about damage control. It's about rewriting the rules of energy and industry altogether. Climate change is, in many ways, the defining story of our time. A story of danger and loss, yes, but also one of innovation and possibility. We've seen the science. We've seen the risks. But we've also seen the seeds of solutions sprouting all around us. And now comes the twist: direct carbon removal, technology that could actually reverse emissions, may soon outcompete fossil fuels themselves. Which brings us to the most radical possibility yet. Because if we can capture carbon at scale, and if we can pair that with the next wave of energy breakthroughs, then everything about our future could change. Not just how we live, but what it means to be human. And that's where we go next. Section 4. The future of energy. Think about this. Every light in your room, every phone charge, every train that runs, every city skyline that glows at night depends on one invisible force: energy. Energy is civilization's heartbeat, and without it, hospitals fall silent, factories grind to a halt, and entire societies collapse. Yet the way we've powered our world for the last 150 years is changing faster than at any point in history, and the race to redefine energy will shape not just our climate, but our economy, our politics, and even our survival. So what's next? Who's building it? And how close are we to a world of limitless, clean power? The giants reshaping our grid today are solar and wind. The sun delivers more energy to Earth in 1 hour than humanity uses in an entire year. Yet for decades, solar power was dramatically underutilized, like catching raindrops in a bucket while ignoring the waterfall beside you. Now, solar panels cost 90% less than they did a decade ago, and in many countries, solar energy is the cheapest electricity ever produced. Wind is joining the charge too, with offshore turbines taller than the Eiffel Tower and blades longer than a Boeing 747, capable of powering millions of homes. In 2022 alone, the world added more renewable energy capacity than all of France's electricity system combined, and China installs more solar every year than the entire United States has in total, with desert megaprojects so vast they're visible from space. Solar panels also thrive in cold, snowy regions, where sunlight reflecting off snow doubles efficiency, while lower temperatures reduce energy loss. Yet even with solar and wind, a fundamental question remains. What happens when the sun sets or the wind stops blowing? Enter the holy grail of energy: nuclear fusion, the same reaction that powers the sun. Hydrogen atoms collide under extreme heat and pressure, fusing into helium and releasing staggering amounts of energy. Unlike current nuclear power, fusion produces no long-lived radioactive waste and carries no meltdown risk, and the fuel, hydrogen from seawater, is abundant, with a single glass enough to power your home for decades. Bottling a star isn't easy, requiring temperatures hotter than the sun's core, but recent breakthroughs are changing that. In 2022, the U.S. National Ignition Facility achieved a historic milestone, a fusion reaction that released more energy than the lasers used to ignite it, marking the first time humanity had broken even. Private startups are racing to innovate further, from magnetic tokamaks trapping plasma inside giant donut-shaped reactors to compact designs that could fit inside shipping containers. Fusion's potential is staggering. Just 1 kilogram of fuel could equal the energy of 10 million kilograms of coal, meaning a single teacup of fuel could power New York City for a day. If solar and wind are today, and fusion is tomorrow, the bridge between them comes down to one problem: storage. Energy isn't just about generating it, it's about keeping it when and where it's needed. Solar panels generate all day, yet demand peaks at night, and without storage, excess energy is wasted while shortages cause blackouts. Lithium-ion batteries, once confined to laptops, now scale to megafarms stabilizing entire grids, and futuristic technologies like iron-air batteries, liquid metal batteries, and gravity storage systems promise multi-day, cost-effective solutions. The world's largest battery, at Moss Landing, California, stores enough electricity to power 300,000 homes for 4 hours straight. Storage transforms intermittent energy into reliable, clean power, but the grid itself must evolve too. Think of it as the nervous system of civilization, where old infrastructure struggles with decentralized renewable inputs. Smart grids use real-time data, sensors, and AI to harmonize millions of energy flows, while decentralized systems let neighborhoods and homes trade energy digitally, creating local resilience and independence. In Brooklyn, microgrids allow residents to sell solar power directly to neighbors, blockchain included, while Japanese towns operate independently on solar and batteries for weeks at a time, a lesson born from the Fukushima disaster. Globally, the energy revolution is surging. Europe leads with Denmark generating over 50% of electricity from wind and Norway almost entirely from hydropower. China, while still building coal plants, is the world's largest investor in renewables, racing ahead with solar and wind. In the U.S., renewables surpassed coal in 2020, with Texas leading in wind energy. Developing nations are leapfrogging traditional grids. India builds solar farms visible from space. Kenya now gets 90% of electricity from renewables, largely geothermal. Imagine a future where solar breakthroughs, ultra-cheap storage, fusion energy, and smart grids interconnect, creating a system where energy is nearly free, abundant, and clean. Entire cities could run independently of fossil fuels, factories fueled by their own wind farms, neighborhoods powered by rooftops, and a planet lit not by burning the past, but by capturing the present. This quiet, steady, unstoppable revolution could be the defining chapter of the 21st century. Yet energy is just one piece of the puzzle. Because if power can be nearly free, what happens to everything else? The economy, work, and the very nature of civilization itself. That's the question the next chapter will tackle. Section 5. The Neuroscience of Decision-Making. Every day, you make about 35,000 decisions. What to wear, what to eat, who to text back, whether to hit snooze just one more time. Yet, here's the twist. Most of those choices aren't truly yours. At least, not in the way you imagine. Your brain, this 3-pound universe of cells, operates on hidden shortcuts, emotional nudges, and ancient survival codes that guide your actions before you're even aware of them. If you've ever paused and asked yourself, why did I do that? The answer isn't a simple one. It's a story of neurons, chemicals, and invisible forces that pull the strings behind every decision you make. Imagine your mind as a courtroom. At the center sits the prefrontal cortex, the judge weighing evidence, planning ahead, and trying to maintain order. Surrounding the judge are a series of advisors: the amygdala, your emotional alarm bell; the striatum, constantly craving rewards and avoiding pain; and the hippocampus, whispering lessons and memories from your past. Together, they argue, debate, and push ideas forward until the judge, your conscious awareness, finally renders a decision. But here's the startling revelation. In many cases, your brain has already made that decision milliseconds before you're aware of it. In the 1980s, neuroscientist Benjamin Libet conducted experiments that confirmed this. His scans showed neurons firing, preparing your actions, half a second before participants realized they had made a choice. Free will, it seems, may be less about choosing and more about vetoing what's already in motion. We like to think of ourselves as rational creatures, deliberate and calculating, yet the truth is far more fascinating. Most of our decisions originate in the emotional brain. Picture yourself shopping online. 2 pairs of sneakers appear on your screen. One is practical, the other just feels right. Chances are, you'll pick the second pair, and only afterward will your logical mind concoct a justification. That's the limbic system at work. Older, faster, louder than the rational cortex. Emotion drives action. Logic merely explains it. In fact, people with damage to emotional centers struggle to make even the simplest choices, like deciding what to eat. Logic alone cannot move us. As one neuroscientist described it, emotion is the steering wheel. Logic is the map. Without the wheel, you never move. Advertisers, politicians, and marketers have known this for decades. Colors, jingles, slogans, all bypass your reasoning mind, hitting the amygdala directly. Red sale tags work better than any price argument, because emotion arrives before thought. Beyond emotion, Your brain loves shortcuts. Cognitive biases are mental heuristics that save time but warp reality. Anchoring bias makes the first number you see stick. A $2,000 watch feels far more expensive than a $500 one if you see the $2,000 first. Confirmation bias makes us seek evidence that supports what we already believe, which is why two people can read the same news article and walk away with completely opposite conclusions. Availability bias distorts perception. A vivid shark attack on TV suddenly makes the ocean seem deadly, even though car accidents are thousands of times more common. Default bias favors ease. The brain chooses the path of least resistance. That's why organ donor rates soar in countries with opt-out systems compared to opt-in. These invisible biases shape careers, relationships, even global events. During World War II, military engineers almost reinforced planes where returning aircraft showed bullet holes. Statistician Abraham Wald realized the true data lay in the missing planes, the ones that never returned. By spotting that blind spot, he saved countless lives. And yet, the story doesn't end with bias. Your brain is also a reward-driven machine. Habits, good and bad, are built on dopamine pathways. Dopamine is not a pleasure chemical, it's an anticipation chemical. It spikes not when we receive a reward, but when we expect one. This is why slot machines are so addictive. Uncertainty fuels your brain, sending dopamine surging through circuits like fireworks. Habits form when a behavior consistently triggers this dopamine response, creating loops of cue, routine, reward, until the behavior runs on autopilot. Brushing your teeth feels effortless, but resisting junk food can feel nearly impossible. Your brain doesn't see good or bad habits, only efficiency. In the 1950s, researchers wired electrodes into rat brains, and the rats repeatedly pressed levers to stimulate dopamine, choosing it over food, water, and even sleep until exhaustion. This accidental discovery illuminated the core of behavioral reinforcement. Yet understanding these mechanisms doesn't mean we are helpless. Neuroscience also offers ways to reclaim control over the mind's invisible steering. Pre-commitment is one tool. Make choices in advance, before temptation hits. Pre-pack meals, schedule workouts, set up your environment so your emotional brain has less influence when decisions arise. Choice architecture is another. Limit options. People are more satisfied when choosing from 6 jams rather than 24. Default settings can be leveraged. Put fruit on the counter instead of cookies. Design your environment so that your brain's natural laziness works for you. Delay the impulse. Even a 10-second pause allows the logical cortex to catch up to the emotional amygdala, shifting outcomes. And finally, pair challenging tasks with small rewards. Study with your favorite tea, exercise while listening to music. Dopamine will learn to crave the habit itself, rewiring behavior in subtle, sustainable ways. One hospital even reduced unnecessary antibiotic prescriptions simply by changing the default from 10 days to 5, a tiny nudge that reshaped behavior across thousands of doctors. The brain is a compass and a trickster, simultaneously guiding us toward survival and clouding clarity. By understanding its inner workings, the courtroom debates, emotional battles, cognitive biases, dopamine loops, and the invisible pull of habits, we gain the rare gift of awareness. Awareness allows pause, deliberation, and the design of habits rather than blind submission to them. It lets us recognize ourselves as more than passengers of biology, more than victims of circumstance, and instead as the pilots of our own minds. And awareness doesn't just change individual behavior. When scaled to society, understanding these hidden patterns shows how entire populations can be influenced by science, technology, and subtle nudges, shaping the way humanity collectively decides its future. Every choice you make, from the mundane to the monumental, carries the imprint of these unseen systems. Yet, with knowledge and deliberate action, you can bend those systems in your favor. You can turn habits into allies, curiosity into strategy, emotion into guidance, and cognition into insight. You can begin to see the invisible currents in your mind, harness them, and steer consciously through a world designed to pull you in countless directions. This is the power of understanding the neuroscience of decision-making. Not merely to predict what you will do, but to expand the space between stimulus and action, to reclaim autonomy, and to navigate life with intention. In the end, the brain remains both a marvel and a mystery, a dense forest of cells firing in patterns shaped by evolution, experience, and culture. Yet the very complexity that makes it a trickster also makes it an instrument of profound empowerment. Awareness, guided by curiosity and tempered by strategy, transforms the unseen mechanisms of the mind from chains into tools. You don't have to be trapped by impulses, biases, or habits. You can observe, choose, and intervene. And as you do, you start to see a larger truth, that your decisions, once thought private and unconscious, are connected to the vast tapestry of human thought, behavior, and society. Every choice echoes, not just in your own life, but in the shared experience of millions, each navigating the invisible currents of cognition together. So the next time you reach for your phone, select a meal, or hesitate at a crossroads, remember, the decision is not simply what you see, think, or feel. It is the cumulative symphony of neurons, emotion, memory, bias, and reward that guides your hand. And by understanding this symphony, you gain the ability to compose your own melody, to pilot your life, not as a passive passenger, but as an active conductor of the incredible machinery within your mind. In doing so, you realize the most profound truth about decision-making. It is not a matter of whether you choose, but how you choose, with awareness, intention, and insight shaping every step along the way. Section 6. Future Tech and AI Breakthroughs. Imagine waking up in a world where your doctor isn't just human, but partly artificial intelligence. Where your phone doesn't merely predict your texts, but forecasts your health risks years before symptoms appear, quietly analyzing patterns in ways the human eye could never detect. Where machines and humans don't just work side by side, they think, sense, and act together, almost as if minds could intertwine. This is not science fiction. This is the emerging reality. The next wave of technological breakthroughs, from AI to brain-computer interfaces, from quantum computing to medical robotics, isn't simply transforming tools. It's reshaping humanity itself. And when these innovations collide, the line between possibility and experience begins to blur. We are living in a world where the future has already arrived, not at some distant horizon, but in the subtle, everyday interactions we often take for granted. Picture a cityscape bathed in the glow of intelligent systems, buildings humming with predictive energy flows, vehicles navigating themselves with uncanny precision, and people connected to machines that sense and respond to their intentions almost before they occur. The pulse of this reality is both exhilarating and disquieting, as if the entire world is holding its breath, waiting to see how deeply technology will weave itself into the fabric of human life. At the heart of this transformation lies artificial intelligence. But AI is not just chatbots, digital assistants, or recommendation engines that anticipate what movie you might want to watch. At its core, AI is prediction, a machine learning to read the language of patterns buried within oceans of data, deciphering trends and signals invisible to the human mind. In medicine, predictive AI is nothing short of revolutionary. It can sift through millions of medical records, cross-reference subtle physiological indicators, and forecast who is at risk for diseases like diabetes, heart failure, or cancer, sometimes years before a human doctor could recognize the first warning signs. One AI system has even outperformed expert radiologists, detecting breast cancer on mammograms with greater accuracy than highly trained human eyes. Another flagged early-stage kidney disease 48 hours before conventional tests could, buying precious time to intervene and save lives. But healthcare is only the beginning. Banks harness AI to spot fraud in real time, cities employ it to predict traffic congestion before it arises, and climate scientists simulate storms decades ahead, offering humanity a fighting chance to prepare for disasters that would have seemed impossible to foresee only a generation ago. Imagine it as a crystal ball, not powered by magic or intuition, but by relentless computation, analysis, and insight. And here's a twist few realize. AI once outplayed seasoned poker champions, not because it could see the cards, but because it learned to model human bluffing patterns better than humans themselves. Machines are no longer just processing numbers. They are learning to understand us, to anticipate our choices, and, in some ways, to mirror our minds. And yet, predictive AI is only the beginning of a deeper integration between human and machine. Enter brain-computer interfaces, devices that blur the boundary between thought and action, imagination and reality. Picture a paralyzed patient controlling a robotic arm with mere thought, or someone who has lost the ability to speak, suddenly communicating through signals captured directly from the brain. BCIs, as they are called, translate the electrical impulses of neurons into commands a computer can interpret, effectively creating a direct line between the mind and the machine. One remarkable case involved a man with paralysis typing entire sentences on a screen simply by imagining hand movements, with electrodes picking up his neural intent. Another individual controlled a flying drone purely through thought, navigating complex patterns of motion without touching a joystick. The implications are staggering. BCIs could restore mobility, treat neurological disorders like depression, and perhaps even unlock new ways of learning, transmitting knowledge brain to brain. In 2019, researchers demonstrated the first cross-continental brain handshake, where a person in India moved another individual's hand in France using only neural signals, a demonstration of direct mental communication that seems to come straight from the pages of science fiction. But with such power comes profound questions. If machines can read our thoughts, if they can interpret intentions and commands at the level of cognition, where does privacy end? Where does control begin? How much of ourselves are we willing to share with the technologies we create? While BCIs expand the reach of human thought, quantum computing expands the reach of possibility itself, bending reality to computation. Classical computers, like the ones we use every day, rely on bits, zeros and ones, binary switches representing a single state at any given moment. Quantum computers, on the other hand, operate with qubits, which can exist simultaneously in multiple states, a phenomenon known as superposition. Imagine reading every book in the library at once, rather than leafing through one page at a time. The potential for this kind of computation is mind-bending. Quantum machines can model molecules in precise detail, paving the way for revolutionary drug design. They can solve planet-scale optimization problems, calculating the most efficient routes for global supply chains. They can even crack encryption codes that currently secure digital communication, a double-edged power that promises both discovery and disruption. In 2019, a quantum processor performed a calculation in mere minutes that would have taken the world's most powerful supercomputer 10,000 years. Yet these systems are fragile, temperamental, and require temperatures near absolute zero to function. Still, their advent is nothing short of a technological ignition, a spark akin to humanity discovering fire, but for the age of information. And within this quantum strangeness lies the key to unhackable networks. Quantum entanglement, once dismissed by Einstein as spooky action at a distance, enables communication channels that detect any attempt at interception, instantly destroying the signal and alerting users, an innovation with profound implications for privacy, security, and global communication. As quantum machines explore the boundaries of logic and probability, robotics is already extending human ability in ways both grand and intimate. When most people imagine robots, they picture industrial arms, humanoid androids, or sleek science fiction companions. Yet the real revolution is happening in medicine, space exploration, and microscopic technologies that expand our reach far beyond our natural limits. Surgical robots operate with precision surpassing the human hand, stitching blood vessels thinner than a hair with unerring accuracy. Robotic systems have discovered new antibiotics, tackling drug-resistant bacteria and potentially saving millions of lives. In space, robotic rovers serve as our eyes, ears, and laboratories on alien worlds, probing Martian soil, analyzing chemical compositions, and sending back insights that guide human exploration. And on a scale almost invisible to the naked eye, nanorobots, machines smaller than a grain of dust, navigate human bloodstream, delivering drugs directly to diseased cells while leaving healthy tissue untouched. These machines embody the dream of medicine at a microscopic level, blurring the line between the biological and the artificial, between intervention and collaboration. Robots are no longer tools, they are extensions of human presence, avatars that amplify our reach into spaces too small, too dangerous, or too distant for us to traverse alone. Yet, every breakthrough carries the weight of responsibility. AI can cure diseases, but it can also automate millions of jobs. BCIs can restore speech, but they can also create new avenues for intrusion into the human mind. Quantum computing can simulate the climate and help prevent disasters, but it can also compromise global security. The paradox of progress is this. The very tools that empower us also challenge our wisdom, our ethics, our sense of control. History provides ample warning. The printing press democratized knowledge and propagated misinformation. The Internet connected billions and amplified both truth and deception. Even fire, humanity's oldest tool, nurtured life and destroyed civilizations. Technology is not destiny. It is design. It is a mirror reflecting the choices we make about who we are and who we wish to become. Consider DeepMind's AI optimization of Google data centers in 2018, which cut energy use by 40%, the equivalent of the carbon footprint of an entire small country, achieved by a single intelligent system. Technology does not just alter efficiency, it reshapes economies, societies, and the very structure of our world. And as these innovations converge, as AI, robotics, BCIs, and quantum computation intersect, they do more than change the tools we use. They redefine the essence of what it means to be human. Already, AI has achieved feats once thought impossible. It has designed novel proteins, crafting solutions nature never conceived, giving humanity new weapons against disease. It has decoded ancient languages, resurrecting knowledge lost for millennia. It has discovered materials capable of creating cleaner batteries, pushing us closer to a sustainable energy future. These achievements are not promises of tomorrow, they are realities of today, unfolding in laboratories, data centers, and research hubs around the world. The story of technology has always been intertwined with the story of humanity. From fire to electricity, from steam engines to silicon chips, each wave of innovation has expanded what humans can accomplish. Yet today, the narrative takes a new turn. Machines are no longer mere tools. They are collaborators, partners in discovery, amplifiers of human cognition, and extensions of our senses and capabilities. They do not merely execute commands, they enhance imagination, unlock potential, and, in some instances, merge with our very consciousness. And so the central question shifts. It is no longer simply, what can machines do? It becomes, what will we become with them? The final chapter of this unfolding story is not about machines. It is about us, humanity navigating the choices presented by our greatest inventions. Each decision will shape the trajectory of our species, whether we merely survive in a world transformed, or whether we embrace transformation itself, leveraging technology to extend empathy, creativity, and understanding in ways previously unimaginable. The fusion of AI, robotics, BCIs, and quantum computing presents a horizon that is at once exhilarating and daunting. Yet it is also deeply human, reflecting our desire to know, to reach, and to transcend. These technologies are mirrors, amplifiers, and companions, showing us not only the possibilities of the universe but also the depths of ourselves. And as we stand on this threshold, it is not the machines that define the future. It is the courage, wisdom, and vision of humanity in choosing how to wield its creations, shaping a legacy not only of survival but of profound, shared transformation. The story is already unfolding. The future has begun. And the question remains, how will we rise to meet it? Closing insights. So let's pause for a moment and take in the journey we've just traveled together. We began by peering into the infinite depths of the cosmos, exploring black holes, those enigmatic engines of creation and destruction, warping time and space in ways that challenged the very limits of imagination. We felt the awe of the universe's scale, where gravity bends reality and light itself becomes a messenger from the edge of the unknown. From there, we returned to our fragile planet, confronting the stark realities of climate change. We saw melting ice caps, rising seas, and dangerous tipping points already set in motion, reminders that our choices today ripple across generations. Yet in the midst of these challenges, we glimpsed hope, the rise of clean energy breakthroughs, from the steady brilliance of solar panels soaking in sunlight to the tantalizing promise of fusion, offering a chance to rewrite the story of power on Earth itself. Our gaze then turned inward, to the most complex universe of all, the human brain. We witnessed how our minds make decisions, how emotions shape our choices, and how hidden biases quietly influence our lives. It was a journey through neurons, synapses, and thought patterns, revealing not just how we think, but who we are. And then, we stepped boldly into the frontier of technology, a place where artificial intelligence predicts the future in ways we once thought impossible, where quantum computing stretches logic to its limits, where robotics extends human touch and capability, and brain-computer interfaces offer direct pathways between thought and action. Each breakthrough was more than a scientific milestone. Each was a mirror reflecting our fears, our hopes, and our relentless drive to understand, to create, and to shape the world we inhabit. It reminded us that science is never only about equations or experiments. It is about humanity itself, about the courage to ask, what kind of future do we want to build? History tells us that every breakthrough holds a reflection of ourselves. The printing press reflected our hunger for knowledge, the spark of electricity reflected our desire to illuminate the dark, and the internet reflected our need to connect across continents and cultures. Today's discoveries mirror something even deeper, our desire not merely to survive, but to transform, to stretch beyond limitations, to reimagine what is possible. Of course, the risks are real. Climate tipping points loom, artificial intelligence brings disruption, and the unknown perils of new frontiers challenge our assumptions. Yet progress has never been a guarantee. It has always demanded courage, the courage to step into uncertainty, guided not only by reason, but by imagination. Each scientific leap is a bridge into the unknown, a bold answer to the question of what humanity can become, and a reminder that the power to shape tomorrow rests in our hands. And that is where you come in. You are not just a spectator. You are a participant in this unfolding story, a member of a community eager to understand, to explore, and to contribute. The journey of discovery does not end with watching. It begins with curiosity, with engagement, with action. This channel is a doorway to that adventure. It is a space for people who seek to make sense of the world and, in doing so, to help shape the future. Subscribe and remain part of the conversation as discoveries unfold. Share these ideas with friends, spark dialogue, and remember that the future is not something we wait for. It is something we create together, through curiosity, collaboration, and courage.